Right, what questions y'all got for me today? Definitely tell I had to move the webcam last week. I mean, no questions works well for me because, still got work to do. I will put this up here just so it's early in the video. Next week is your final exams. I'm not going to do any live streams. If you want to talk in person, we can schedule a time to do this via Teams. I'd really much rather you stick to emails. We're kind of in a weird situation. To give you this extra week in this semester, we got rid of the break between spring semester and summer semester, and I'm teaching this summer, which means that after you all take your finals, I submit your grades, I turn around the starting Monday, and I start teaching Chem 2 again. So I am here to answer your questions. Emails are a lot more convenient for me simply because I am having to set up the course shells for the summer next week. That means getting all the discussion boards together, all the exams prepped, all the course releases done. So there's a lot going on my end, and I'm not 100% sure when I'm going to be available while I'm trying to set this up. Again, I'm here to answer your questions, although I would kind of like to refrain from the face-to-face if it's possible. If you need it, we can schedule a time. But again, I got a lot going on next week, and it's a lot faster and easier to respond to emails. That said, also keep in mind you will have all of next week to take your finals starting Monday 12:01 a.m. up until Friday at 5 p.m. But that 5 p.m. number is referring to when you should be finishing the exam. You have an hour and 50 minutes to take your final exam. So at 3:10 p.m. on Friday, Blackboard will lock you out. Blackboard will not let you take the exam if you don't have enough time to finish it before the due date. I will not be granting extensions. You have more than 5 days to take this exam. Please go ahead and get it out of the way. If you don't get the grade you want in the course and you take the exam Tuesday or Wednesday, there will be time for you and I to talk about it. Maybe we can go back and regrade an assignment or two. But if you take your final exam Friday at 3 o'clock in the afternoon, and you're going to see this in the email next week, after about noon on Friday, I'm not going to really hear out any requests for grade changes unless you can really demonstrate to me that there was an issue with how the final exam was graded. I am going to go through and check the final exams to make sure that all the answers make sense, but I'm not going to, like, at Friday at 5:30 sit down and have a discussion with you about improving your grade. And the big reason is, again, because we had this week extension this semester, I'm turning in grades Friday afternoon. I have to. So I don't really have time Friday afternoon with going through exams, submitting 4 sets of grades, to really go through and talk to you about your grade. You need to get this in as early as possible. So if you have concerns about your grade, we can talk about it. This is not to be malicious. This is not to be condescending to you. It's just a statement of fact. Friday evening, I have to get my grades in. So the plan is Friday at 5 o'clock, look through all the final exams that were submitted at the last minute, get the grades into the grade book, get them into Blackboard, and get them submitted to WebAdvisor. I'm not going to have time Friday afternoon to answer your questions about your grades because it's not just your class, it's not just your section. Got to do this for organic, got to do this for 132, got to do this for both the 250, 152 sections. So again, take your exam early, get it out of the way. If anything, it's just stress off of you. All right, I'll give you about 5 more minutes. If you don't have any questions, we'll just shut down the live stream for today. Stuff from last week. Can you be a bit more specific about what stuff you're struggling with? Yeah, discussion board for Wednesday we can definitely talk about. So let's go to the discussion board from last Wednesday. So in 427 we talked about this reaction, 8 hydrogens plus the permanganate plus the 10 goes back and forth to 4 waters, manganese plus 2 and 10 plus 2. And there's 4 questions that ask you. First of all, what's the standard potential? Next question that asks you is how many electrons. It asks you for Q, and it asks you for the actual voltage of the cell itself. Now, I'm going to write these numbers down. We have 0.1 molar SnCl2. We have 0.20 molar what was that compound? Manganese 2 chloride, and we have 0.01 molar HCl. So in terms of the standard reduction potentials, what we would need to do to figure that out is actually go through the tables of reference voltages. We need to identify the oxidation and reduction reactions. So in this case, we have manganese plus 8 going to manganese plus 2, and we have 10 going from 0 to plus 2. Now, on the final exam, there's actually a downloadable Word document. It gives you all the reduction potentials. It's much more focused. On the course website, what you would need to go to answer this question, and actually a lot of the questions that are online on the homework, is under lessons. Final exam. At the very, very bottom, well, close to the bottom, there are tables of standard redox potentials. And this is what you would have to go through to find the redox potentials. Now, like most tables, it's organized 2 ways. It's organized by voltage and it's organized by the element. Mercifully, it's organized by element first. So if we scroll to the list, we have this MnO4. There you are. MnO4, 4 plus H goes back forward to Mn plus 2. That's 1.224 volts. And our 10 reaction, Sn, Sn plus 2 to Sn is minus 0.1375 volts. So To figure out the standard reduction potential, it's the potential of the reduction reaction minus the potential of the oxidation reaction. Now, these are standard reduction potentials, meaning that it's what the reaction would be if we reduce. So the reason we're subtracting off the oxidation reaction here is that this is its reduction potential. To flip a reaction to oxidation, we just take the reverse of the reaction, which flips the voltage. Manganese here is being reduced, so it's 1.224 volts. Tin is being oxidized, so it's minus negative 0.1375 volts. So when we do that, we get 1.36. You can either do 1 or 2, or 1.362 or 1.63 volts. So that's your first question. What's the reduction potential? Second, how many electrons are transferred? This is a balanced redox reaction. I would never give you a problem like this and say, hey, go out and balance the redox reaction. Because if you get it wrong, it kind of messes with the rest of this analysis. Two ways we can do it. We can look at the oxidized species or the reduced species. The reduced species, we have manganese going from +8 to +2. That's 6 electrons. For tin, SN, we have it going from 0 to +2. That's 2 electrons. But there's 3 manganese atoms doing that, so 2 times 3 is also going to give us the 6 electrons. Q, calculated the same way you did for test 3 and test 4. You've got your expression for Q. It's concentration of N, concentration of manganese, all over the concentration of H plus to the 8th power. This ends up, I think, giving you 10 to the 12, 2 times 10 to the 12, something to that effect. The voltage of the cell, the E cell here, that's just your Nernst equation. So it's your reduction potential, your reference voltage, E naught cell, minus RT over NF, ln of Q. So you got your value for Q. R here is 0.008314 kilojoules per mole Kelvin. T here, the temperature is given to you is 25 degrees C, so it's plus 273 because you've got R, that'll give you 298. N is the number of electrons transferred, so there's your 6. And F is Faraday's constant, 96.485 kilojoules per volt equivalent. So that's how you do the discussion. That's how you do the discussion board from last Wednesday. To answer Abby's questions, the discussion board isn't letting you answer. Let me take a look at that. I can do it now, but probably after we do the live stream, since you can answer discussion boards anytime. We will not have a live stream Monday. I would prefer you send me emails. If you really need to meet face to face, that's fine. I actually have to do 2 things next week, which I normally don't have to do at the same time. One is I have to go through and start grading all your exams. The second is I have to start setting up my summer course, because actually the week after your exams is when summer course starts. Usually we get a week gap so we can do the course setup separate from our exam grading. Because we lost a week due to the pandemic, I'm now having to do both at the same time. So the live streams, if there's really a push, we can maybe negotiate doing 1 live stream next week. But I kind of need to focus my efforts on getting the exams graded, getting the grades in, and also kind of setting up my summer course, because it is the first Monday after your exams next week, we start the summer sessions. May 15th as well. Actually, the lab practical should be due this Friday at 5 p.m. I think that's the way I set it up. So you have this week to complete the lab practical. This way I can go ahead and get your lab grades finished up. But you have until Friday at, I think it's 5 o'clock, it may be midnight. Let me take a look really quick. Because you're also going to email about this as well. So yes, this is due this Friday at 5 p.m. So your lab practical is due this week. So the discussion board this week. So we'll switch back to that. So balancing nuclear reactions is actually pretty trivial. That's why I like saving it to like the last week. Because I'm typically in normal semesters when we're dealing with, at this point in the semester, typically y'all are dealing with a lot of last minute projects. So I like my class to kind of be the easy one. So we got uranium-238 with 92 protons, goes to helium or alpha particle and some decay product, question mark. So to balance nuclear reactions, there's only three things you can really look at. The first is that the total rest mass, so this is the sum of the weights of the protons and neutrons, assuming they are by themselves, has to add up on both sides. So we've got 230 on the left, and we've got 4 here on the right. So whatever we have when we add 4 to it, we should get 238. So it's 234. Same thing is true of nuclear charge. So we've got overall charge. So we've got 92 protons here. 2 here means that whatever is here has to have 90. So 90 plus 2 gives us the 92. The only other thing we have to work out is whatever this compound is. And from chemistry 1, this number here is your atomic number. So whatever element this is has atomic number 90. So this will give you thorium. Malika's asked, in our lab notebook for calcium iodate for the procedure section for pre-lab, are we writing it based on what is in the lab manual or what we wrote for part 2 on the assignment sheet? You're going to write, so the lab manual at this point is no longer being used, so you're going to write out what you did for the virtual lab. So everything pre-pandemic, pre-spring break, that's going to be your normal expectations for pre-labs and post-labs. Afterwards, it's just basically transcribing the virtual lab into your lab notebook. Traditionally, what happens with online courses is that there is actually a take-home lab kit. You buy it, you use it, there's procedures, there's pre-labs and post-labs, it's a bit more flexible. You are not an online course, it's about $300 for that lab kit, and as a school we made the decision that would be kind of shorting the seated students, that halfway through the semester you're going to get stuck with a $300 bill, and you're only going to use half of that $300 kit anyway. So it's kind of weird, but it's just what we're going to have to do. But yeah, for the online labs, just transcribe in the online labs into your lab notebook. And just for my own edification, I think the lab notebooks are due this Friday as well. I did not put a due date on it, but I did put a display date on it. So you will not be able to submit your lab notebooks after midnight on Friday. So again, I do need to update the due date so you can see it in Blackboard. Oh, it's for the Redox lab this week? Yeah, same thing. Just basically what you did in the simulation. But yeah, Friday at midnight is when your lab notebooks are due. This way I can spend next week compiling all your lab grades and give you a final grade on the course website for your lab grades. Now, throughout the week, for my sanity, I'm going to be grading the practical, I'm going to be grading the lab notebooks, I'm going to be grading the Nernst labs. As soon as I get everything for you, I'm going to start loading your lab grades to the course website. Yeah, it's weird because FET posted this and posted and maintain it. So a lot of you have sent me emails asking me about the last 2 videos on the Nernst lab. Just skip them. It looks like FET took them down and didn't bother to update their sheets. So I'm not going to take off points if you didn't do it, especially if you couldn't find them. So just ignore that last part that tells you to look at those videos. What are antineutrinos? Those are neutrinos with a negative neutrino mass. So neutrinos are kind of weird. They were thought to be massless. They're not. They have a vanishingly small weight, but they do weigh something. What's unique about neutrinos is that they look like they have a negative time component to them. So whenever a neutrino is created, there's both a neutrino and an antineutrino created. The neutrino itself travels backwards through time, or at least it looks like it goes backwards through time, whereas the antineutrino looks like it goes forward through time. Now, because of this, we get conservation of mass and energy with neutrinos. So when they're created, their particle and antiparticles are created. When they meet up in terms of their timelines, they're annihilated. So basically, an antineutrino is what's created when a neutrino is created, and it's in the opposite direction. They have negative masses, so when they do find each other, they annihilate. Now, I'm not remembering off the top of my head exactly, but I think every time a neutrino is created, its antineutrino is created at the start of time. There's something to that effect, where they annihilate each other at some point. So there was theoretical discussion about using neutrinos for basically basically talking backwards in time, so sending messages back. There is, because of how neutrinos work out in terms of Schrodinger's wave equation and how they work out in particle mechanics, they can't be used for that, because I think in order to measure a neutrino, you inherently destroy it. So there's no way to keep information going with a neutrino. But it's been a long time since I've talked and looked at neutrinos. But yeah, I think the antineutrino, it is a neutrino with a positive time component, whereas a neutrino has a negative time component. And I definitely know they're generated in pairs. When you generate a neutrino, you inherently create an antineutrino to go with it. So Elijah wants to do the first Nernst Equation program on the WebAssign. All right. So let's go back to the course website. I have had issues of this interface not letting me move down. And it looks like that's still the same issue. So I may actually have to switch to my desktop to make this happen. So let's switch to my desktop. So here we have the Nernst equation, number of electrons. So the reaction here, 2H plus 2He HFE O4 minus 1 plus 3 ClO minus 1 goes back and forth to 3 ClO2 plus Fe2O3 plus 2H2O. So in terms of figuring out the number of electrons transferred, the challenge here, both of these have not one coefficients, they have greater than one coefficients. So the oxidized and reduced species, because this is a balanced redox reaction, have to have the same number of electrons transferred. So iron here is in a +7, and down here it's in a +3. Here we have chlorine in a +1 going to a +3. So we have to look at the number. It doesn't look right. It is right. So we have to look at the number of electrons transferred. So we've got. Did I transcribe that wrong? That would not surprise me. Three, 7, 6 electrons, and I would agree with that. So the easiest one here to work with is the chlorate. So we have chlorine going from +1 to +3. That's 2 electrons, and we have 3 doing that, so that will give us 6 electrons. Now, why is this making me question myself? Looks like that one isn't quite right. Because that's 7 to 3 gives you 4 electrons, and it gives you 2, so that would be 8 electrons. My guess is that's actually supposed to be HFeO3. But that doesn't seem right. I'm thinking it's not supposed to be Fe2O3 at the end. I think it's supposed to be FeO4, would be my guess. So if you're getting 8 electrons, I can see where you're getting that. The intention here is 6 electrons, so I'll take a look at that problem. But yeah, based on chlorate, it should be oh, thank you, Isaac. It's not +6, it's actually +5. Oh yeah, +6. So that was my mistake. So yeah, it goes from +6 to +3. So that's also 3 electrons, but we've got 2 iron atoms doing it, so that will give us 6 electrons. So based both on the oxidation and reduction reaction, you get a 6 electron transfer. Where will we see the formation consumption of positrons? So yes, positrons are a form of radioactive decay. They're pretty rare. NC State actually has a lab. Their nuclear lab generates positrons for what's called antimatter spectroscopy. Not 100% sure how that technique works, but basically, where you would see it, a nuclear reactor, particularly reactors where they're trying to generate isotopes that they know go through positron emission. I have rarely seen positron capture because what the positron has to do is it has to pass through a whole wave of electrons to get to a nucleus. So typically what happens is that when this positron is ejected from the nucleus, it hits one of the inner electrons, annihilates it. So matter-antimatter interaction generates the gamma ray, and that makes it all work out. But yeah, positrons, we have to work with certain nuclei. I don't require you to memorize what the different decay pathways are. I don't think that's particularly useful. There are tables of it if you're particularly interested, but that's why we have tables, that's why we have Wikipedia, is so we don't have to memorize all these different decay pathways. Okay, Abby, what's your random question? Do I have a grade calculator determining what we need to get on the final exam to get a grade in the class? Yes, actually, my grade book is actually designed to do that, and on top of that, it actually sets up what you have to get on the final exam, as well as probabilities. So to figure this out, and you would need to wait until about Monday or Tuesday when I finally got all the grades up to make this happen. The final exam counts for 22% of your grade in the class. So to figure out the minimum you would need on the exam, or basically take the number of points it takes to get a grade. So an A would be a 90, B with an 80, C 70. I guess if you're shooting for a D, there's a 60 in there. Once you have your final grade. So right now, when I do your homework and when I do all those assignments, it's only 22% of the grade. It's going to be your grade, which we'll represent with a G here. G times 78% plus your final times 22%. So if you want to figure out what it takes to get an A in the course, take 90 minus your grade times 0.78 divided by 0.22. To get a B, 80 minus your grade times 0.78 divided by 0.2. To get a 70, 70 minus your grade times 0.78. So whatever your numeric grade is in the course, so there's that weighted total column and the letter grade, which I haven't assigned yet. Take the grade you want, and this is the minimum you need on the exam. Subtract your grade times 0.78 and divide by 0.22, and that's what you would need to get on the final exam. Now, remember, you cannot possibly get higher than 100 on the final exam. In fact, if he tells you like, oh, you need like a 98, 96, you're probably not getting that. Like, full disclosure, probably not getting that. But something like a 70 to 80, what I found is typically on final exams, students do on average 10 points worse than their test average. This is actually kind of a weird competing effect. So A students do worse on the final than they do on their test averages. B and C students actually do pretty close to their test average. Then D, F do lower. This effect, the A students don't need to do well on the final, so they don't have to, and they typically don't. B, C students typically are trying to keep their grades in the class, so typically they're a bit more on par with their test average. Now, as far as the standard voltage on that WebAssign problem. So give me just a minute to reset my browser in OBS. And this is being particularly aggressively bad. Okay, so I'm going to send you back to the problem. So let's switch to the desktop really quick. And really the big thing we need from this reaction are the oxidized and reduced couples. So we have H FeO4 minus 1 coupled with Fe2O3. And we've got ClO1 hypochlorite paired with chlorite. So to determine what the actual reduction potential is, with this one you're probably actually going to have to go onto the course website under lessons. Final exam, electrochemistry and nuclear chemistry. And towards the bottom you have the table of standard reduction potentials. If we look for the HFeO4, and this is first part of this is arranged by element, that's 2.09 volts. And for the chlorite hypochlorite combination, we're looking for one that has both of them in it. And it's going to be this one here, 0.66 volts. So to determine what the oxidation potential is, we have to figure out who's being oxidized and who's being reduced. So here we have chlorine going from +1 to +3. Here we have iron going from +6 to +3. This is the reduction reaction. This is the oxidation reaction. So it's the reduction reaction minus the voltage of the oxidation reaction. So we have 2.09 minus 0.66, so this will give us 1.43 volts. And being extra generous, the key will take 1.44 and 1.42. So that's how you find the standard reduction potential. Traditionally, when we write batteries, so this is something that we don't talk about online, it's more important you focus on that. This is typically how battery reactions are written, because the overall reaction isn't particularly interesting unless you need to know if it's acidic or basic. But here's your reduction couple and here's your oxidation couple. Lab practical difficult. I think it's much more straightforward than the practical you would have taken. That said, it's a bit more out of the left field. So it's hard in the sense that a final exam is hard, is that there's so many different ways the materials can be presented. You don't appreciate until you take a general exam versus a focus exam. Each of our tests have been focus exams, which makes it easy to study for. This lab practical covers everything. That said, you're getting a resource with this practical that you didn't really have for the lab, which is you've got the internet. You've got your notes. Usually you only get your lab notebook for these practicals. Part of the reason I don't think this practical is fair when you take it in the class is that, and you can kind of see this, it's kind of like non sequiturs. It's like, oh, how do you do this? It's like, okay, but what are you like getting at? Like, where would I have seen this? And once you know where you've seen it, it's not too bad. So parts of it are difficult, particularly the ones that draw back to Chem 1 materials. So there's one about Beer's Law. If you haven't done Beer's Law in a while, it's kind of a struggle to get there. But I think for the most part, it's not bad. You definitely have more time to take it than you really need. I would say probably an hour and a half to 2 hours to take it, but you get the full 2 hours and 50 minutes. But again, I've also had people tell me it's just a super hard practical, even online versus seated. So I would lean it's towards the hard end, but I would not say it's like super hard, unfair. Just, it's a lot. Unfortunately for you all, I already had this one developed. My Orgo students actually got lucky. I put some extra credit on it because their labs have been utter disasters this semester. So I'm feeling merciful to them. Y'all kind of actually not too bad this semester in terms of your labs. I mean, yeah, they've been canceled, but like only 3 were actually canceled. Personally, I would have preferred for you to present videos this semester and show me videos of you doing a presentation with your lab partner on a lab you did this semester. 2 major issues with that would have been, one, how do you and your lab partner collaborate on an online presentation? The second, the more interesting labs come towards the end. So how would you give a presentation on some of our earlier labs? Because there's more groups than there are labs to go around. So yeah, sorry on that. The goal of the plan of the semester was to get you to do like presentations in the lab and do like actually talk about a lab you've done previously in the semester. So maybe this summer. Well, since I've got y'all here, let me take a look. I'm not going to show you the lab practical, but I will tell you what's on it. One is a question you asking to match the concepts associated with the labs. How did you determine molar mass by freezing point? So there's definitely that lab. Question on IMFs. 2 questions on IMFs. The Chateliers principle. A question about the iron titration lab. Finding KQ from calculus. This goes back to your iron thiocyanide lab. A question on molarity. A question on rates of reactions. Questions about standard deviation. Questions about Le Chatelier's principle from that online in Le Chat's lab. Question about intermolecular forces. Ooh, I need to get rid of that question. Yeah, I'll probably just give you all points for that one. Question about rates of reactions. Another one about the iron titration. Another one asking you about the freezing point lab. Kinetic analysis, titrations, and more on rate laws. It's 20 questions. Honestly, most of these you can answer without ever having done the lab. There's only a few on here that are truly lab specific. But again, you've got 2 hours and 50 minutes. And yeah, feel free to go back and rewatch this video. Practical is not meant to be a gotcha kind of test. It was more meant to help you study for the practical before you took it. And I see now there's only one question that's not really fair, so I'll just give you all the points when I go. I'm going to go through and grade the exams by hand anyway, just to make sure there's nothing like glaringly wrong with the key. Nuclear decay is nearly impossible to make hard. The hardest I can make it are half-life problems, and even then, you use the half-life formula if that's it. I don't think I give you the half-life formula. It's in the notes. But you can't make it hard because of conservation of mass, and you can't make it hard because I'm not going to require you to memorize decay pathways. I think State used to kind of do that to haze their incoming freshmen, that you had to memorize the decay pathways for uranium or something like that. But what you're seeing in terms of the packet problems and the homework problems, that's really as hard as it gets. That's why I asked you in the problem, like, how could I possibly make this harder? And there is one hard example in the homework, which is nitrogen absorbing an alpha particle to give you oxygen. It's hard because you have 2 nuclei, but that's the only case where I've ever seen of alpha capture. So these problems don't get hard, and it's just because we simply don't understand the nucleus very well. We can't probe it. So we have a lot of basically the engineering side of science where we can tell you what has happened historically, but as far as making predictions and making it hard, we don't have the ability to. Now, in terms of a half-life problem, let me bring up one of the packet. Let me bring up the packet. Well, let's see if OBS is going to play well with the Word document today. Nope, doesn't want to play well. So there is a first problem on the packet. You have a 23.7 gram sample of molybdenum 98. And it has a half-life of 0.684 hours. And the problem asks how much remains after 0.961 hours. So if you go to the packets, half-life problems, it's on page 13. The way we do a half-life problem is we just use the half-life formula. So the concentration or the number of atoms or the mass, doesn't matter, they're all related through simple conversion factors, equals the starting amount times 1/2 raised to the time divided by the half-life. So we want to know how much remains of a 23.7 gram sample after 0.961 hours if the half-life is 0.684. So to figure that out, we'll just take 23.7 times 1/2 raised to the 0.961 divided by 0.684, and that will get us back to the amount that remains. The only way to truly make this type of problem hard is to make you solve for something like time or half-life. In the notes, I give you a formula for it, and basically it's like the natural log of the starting concentration over the final concentration over the ln of 2 equals time over the half-life. Again, it's a formula you're going to have access to during the final exam. It's just algebra. But yeah, generally speaking, half-life problems are plug and chug. Find out what variable I haven't given you. I've given you the other three, and solve for the unknown variable. I'm wondering if your last discussion board is up or not. So redox problem, you mean balancing redox or like Nernst equation redox? So let's do a balancing redox. We'll do a half reaction, a full reaction, and a Nernst equation. So I'm going to share my desktop. Well, actually, not right up. So for the half reaction, this is in the packet. It's magnesium hydroxide. Goes back and forth to solid magnesium. for half reactions, you're going to manually change out, you're going to manually add the electrons to one side or the other, because with a half reaction you get oxidation or reduction. So you can just kind of put in whatever you want. As with all these problems, the first step is to figure out the oxidation state. We're going to treat oxygen as -2 and hydrogen as +1. Reason being, it's just a lot simpler. This is going to be true in higher division courses, but don't worry about it. For now, the idea is understanding the concept. So magnesium hydroxide, OH here is a -1 charge, so this puts magnesium in a +2. Magnesium here is in a 0. So to get our charge to work out, in order for magnesium to go from a +2 to a 0, that's reduction. And we need 2 electrons to make that happen. Now we're going to balance oxygen. So we have 2 oxygens on the left, 0 on the right. So we're going to add 2 water molecules to balance out the oxygens. Last step, balancing out the hydrogens. We've got 2 here, we've got 4 here. So we're going to need to add 2 H pluses on the left side to balance out our hydrogens. So now we have a balanced half reaction redox. Big difference between a half reaction and a full reaction. With a half, you're going to finish with electrons. With a full redox, you shouldn't finish out with any electrons. For a full redox, we'll do the second example in the packets. So we have F2 plus I2 goes back and forth to HF and HIO. Again, with all redox problems, we're going to start by figuring out oxidation states. Anything by itself, unless you see a charge. These are both 0 oxidation states. Fluorine here, the biggest, most electronegative element in the periodic table. It's not bound to itself, it's a -1. Iodine here is in a +1. So now we have to figure out our oxidation and reduction couples. So fluorine is being reduced. Iodine is being oxidized. So we have F2 goes back and forth to HF. This is 0 to -1. Iodine, we have I2 going back and forth to HIO. This is iodine from a 0 to a +1. First step, you absolutely have to do this with all redox reactions when you split them into these halves, is you need to balance whatever is being oxidized or reduced first. We are not going to follow what the book recommends and what you have still have access to it, what the ILC recommends. We're not going to balance oxygen or hydrogen until we get back to the full reaction. It's just extra work. So here we have 2 fluorines on the left. So we need to put a 2 here to get us our 2 fluorines on the right. So now fluorine is balanced. For iodine, same story. 2 on the left. So we need to multiply by 2 to give us 2 on the right. Now we need to count the number of electrons. We have fluorine going from 0 to -1. That is 1 electron. And we have 2 of them doing it. So because we have, I'm sure I can actually see myself. Because we have two fluorine atoms, each gaining 1 electron, that's 2 electrons total. And since it's reduction, we're going to put the electrons on the left side. Iodine, same story. 0 to 1, that's 1 electron. There's 2 iodines doing that. So that gives us a total of 2 electrons. Now, at this point, we want the number of electrons gained by reduction to equal the number of electrons lost by oxidation. In this case, they happen to be the same number. I'll close my window. So, luckily it's 2 and 2, which means when we add these reactions back together, they cancel out. Hypothetically, so not for this problem, but let's say this ended up being 1 electron here. If this was 1 electron, we would double this reaction. So there would be 2 electrons lost and 2 electrons gained. The idea here is at this point, each half reaction itself is balanced in terms of electrons. We just need to make sure that the number of electrons gained and lost equals each other, so we're going to multiply each reaction by some integer to get them to that point. But since they both have 2 electrons, we can add them together. They'll cancel out, and we'll get a 2 in front of the HIO and a 2 in front of the HF. Now we're going to balance the oxygens and the hydrogens, and we're going to start with the oxygen first. So here we've got 2 on the right, 0 on the left. So we need 2 water molecules on the left to balance out the oxygens. So 2 and 2. Now, mistakes students typically make is that they're going to say, well, I got 2 water, so I need to add 4 H pluses to the right side. That's not true. You need to actually go through and do an accounting of it to make sure. So here we have 4 hydrogens on the left, and we have 2, 4 on the right. So now our hydrogens are balanced. And at this point, we have a balanced redox reaction for fluorine and iodine. The last problem, the Nernst equations. So I'm going to balance between the solution set, which you have access to, just because I don't want to go look up the tables. So the first Nernst problem, it asks you to figure out the reference voltage of the cell, the E0 cell. So you have 2 reactions here. You have sulfur being oxidized from -2 to 0, and chlorine being reduced from chlorine +3 to chlorine +1. So those are 2 electrons being transferred. You would go to your tables or redox potentials, look up these voltages. The reduction reaction here is chlorite to hypochlorite, so ClO2 minus to ClO minus. That's 0.66 volts. The oxidation reaction is sulfur -2 to sulfur. That reaction is -0.0476 volts. You're going to subtract the oxidation reaction, and this will give you 1.136 volts. Now, in terms of finding the actual voltage, calculate E if all the concentrations of the aqueous species are 0.2 molar. So let me write up the reaction up here on my board. So in order to find the voltage of this, we're just going to need, well, we're going to use the Nernst equation. So it's E0 cell minus RT over NF ln Q. So unlike the homework, this is kind of not guiding you as well. These packets were more meant to be done in class. So E0 cell you already have. That's your 1.136 volts. R, physical constant, 0.008314. The temperature was given to you as 25 degrees C. You had to convert to Kelvin because you have an R. So that's 298 Kelvin. Faraday's constant, 96.485. The number of electrons transferred. This is actually a pretty straightforward problem. We have sulfur going from -2 to 0. So you've got 2 electrons. The only thing in here that requires any like substantial effort is Q. So Q in this case is the concentration of ClO minus 1. I'll have the concentration of ClO2 minus 1 times the concentration of H plus squared times the concentration of S minus 2. Now it tells you in the problem all the concentrations are 0.2. The reason I give you that example first is that it kind of makes the math really easy. You've got 0.2, 0.2, 0.2, 0.2, so this is 1 over 0.2 to the 3rd power, and when I worked it out, Q is 1 over 0.008. Now, when you plug this into the Nernst equation, your voltage here is 1.074 volts. Now, the only true way to like make these Nernst equation ones super hard is to give you weird concentrations, so Q is not as easy to figure out. But the reference voltage, you can see, you just go to your tables, subtract the reduction reaction from the oxidation reaction. RT, NF, you should be pretty comfortable with at this point, particularly with the number of electrons transferred. Like if you've balanced redox reactions, you know how to do this now. Q is the only challenging part of the Nernst equation. Because in order to find Q, you have to take the expression and plug in all the concentrations and make sure you've got the right powers. But there's the full sweep of redox reactions. Balancing a half reaction, balancing a full reaction, and using the Nernst equation. The other one we have is the plating reaction. And we've talked about that in a previous video. Do you want to go over current and mass and how to find basically how much anode cathode material is lost or gained depending on how long a reaction is run and how much current is being drawn? Yeah, you're welcome. Okay, so for the plating reaction, or I'm sorry, the electrolysis, or however many other ways you want to talk about it, we have a general formula. The general formula is I times T times 1.037 times 10 to the negative 5 times nu of what we're interested in divided by nu of the electrons times the molecular weight of I equals grams of I. So this 1.037 times 10 to the negative 5, that is a conversion factor, and it is a whole bunch of conversion factors all up together. So it's Coulomb's constant, it's Faraday's constant. The idea here is that your current I is in coulombs per second, and it has to be converted to electrons per second and then moles of electrons per second. The T here is the time in seconds, and I here is the amperage, or amps. This 1.037 10 to the negative 5, if you go look at my notes online, basically at this point you are in units of moles of electrons. So multiplying I times T times 1.037 times 10 to the negative 5 will get you to units of moles of electrons. If we have any reaction where we have some metal and we add in electrons to it to get it to like a zero oxidation state, your nu E here is the coefficient on the electrons. Your nu of I is the coefficient on whatever you're interested in. So in the practice packets online, there's a question: if zirconium plus 4 is plated onto a surface for 60 seconds at 1.2 amps, what mass of zirconium is ultimately plated? So in this case, we have zirconium plus 4 going to zirconium metal, and we've got 60 seconds and 1.2 amps. So these again are very plug and chug kind of problems. You're given the current is 1.20. You're given the time is 60 seconds. The only way to really make this challenging is to give you not seconds, but I don't really see a point doing that. So 1.2 times 60 times 1.037. Zirconium is being plated as a metal. So to get rid of our plus 4, we need 4 electrons. So our coefficient on the electrons is 4. We have 1 zirconium atom, so it's 1 over 4. And then to figure out grams of zirconium, so that MW sub I, we need to take the molecular weight of zirconium. Now, later problems I think in the packet ask you to solve for like current and time. Basically, you just have one unknown variable, but it's this formula every single time. I don't know how other instructors teach it. I also don't know how a lot of the online resources teach it. I do in the notes go through the derivation of the 1.037 times 10 to the negative 5. That said, I think it's a lot of detail for a very simple conclusion. So if you're kind of losing the forest in the trees, like, well, how do I get from point A to point B? You can just rely on this formula. It's on the formula sheet I give you. But it is basically a whole bunch of conversion factors lumped together. So where the 1.037 comes from. Okay. So if you look at first part of the equation, I times T. I is coulombs per seconds. And T here is your time in seconds. So if we multiply the current times the time, we will end up in units of coulombs. So at this point, and I'm just going to put the marker here, we are in units of coulombs. Now, there is a conversion factor between, so the number itself is 1.037 times 10 to the negative 5. There is a conversion between coulombs and electrons, because the coulomb here is the charge, and there is a coulomb associated with electron. And I want to say it's given the variable uppercase C. I don't know off the top of my head. So if we multiply by this conversion factor, this takes us from coulombs to electrons. But that's not particularly useful because that's numbers of electrons. I'll get back to you, Ryan. So the next thing we have to do is divide by Avogadro's number, Na. And this takes us from electrons to moles of electrons. So once we multiply by this conversion factor to give us from coulombs to electrons, we're going to divide by Avogadro's number to get us to moles of electrons. From there, we're just working in moles. And so for any reaction, if you want to convert from one thing in a reaction to another, you take the reaction coefficient of where you're starting. So in this case, we're starting from electrons, and we want to take the moles of electrons. And it's times wherever you want to go. So dividing where you're coming from by where you want to go. Nu I is whatever we're interested in, whatever metal we're plating or removing. Nu E is the number of electrons. This will get us to moles of species I. After that, we just multiply by MWI, molecular weight of I. So to go from moles to grams, you just multiply by molecular weight. And this puts us in grams of I. Now, if you take this charge conversion between an electron and a coulomb and divide by Avogadro's number, the product of these two is 1.037 times 10 to the negative 5. And if you're looking for units on that, that would be moles of electrons per coulomb. But all of that C over Na, that's where that 1.037 times to the negative 5 comes from. It's just two conversion factors. One to get us from coulombs to electrons, and one to get us from electrons to moles of electrons. And to answer your question, Ryan, it's not Mn, it's N as in Mike, W as in whiskey, Mw sub I. That's the molecular weight of whatever species you're interested in. So if you've got something like zirconium, I here is going to be zirconium, so species I, we need to multiply by the molecular weight of zirconium. Well, you can see, it's easy to get lost and lose the forest in the trees with this kind of formula. That there are two conversion factors here. I don't know them off the top of my head. Well, I know Avogadro's number, 6.02 10 to the 23rd. But I don't remember what Coulomb's conversion factor is. So be cool to have it, but honestly, if you lump the two of them together, it's a much simpler number to work with, because this is some like teeny tiny number as well. Any other questions? Final exam, go back and study all the old packets. Understand the questions that you're going to get asked are not nearly like the level of difficulty I ask. The one I would spend the most time on, because I see students miss an odd number of questions on that, is go back and look at intermolecular forces and functional groups. There are several questions about that in the final exam. Conceptually, it's not hard, but it's also easy to lose it because typically with me, you're used to the more challenging like algebra problems. This final exam was not written entirely by me, at least the one you'd be taking class. The one that's online is inspired by the final exam, so it's the same concepts. But again, you got 35 questions. The problems cannot be nearly as involved as they are on a traditional exam. So I would say the qualitative concepts, particularly with IMS and functional groups, so that test one material. But the other well-represented sets of questions on the final exam are equilibrium problems. So acid-base equilibrium, solubility equilibrium, those are the types of questions you need to be looking at as well. Less challenging, in my opinion, just because typically most students really get kinetics. There are several kinetics questions on the final exam. They are not going to be, they're a lot more approachable. They're meant to be much more solvable. That said, don't get sloppy, don't get arrogant. Do know your zero, first, second order reactions. Do know how to do the analysis, method of initial rates versus graphical analysis, and be able to do those. But yeah, traditionally what I see a lot of students have forgotten at this point is IMFs, intermolecular forces, simply because one, we cover that like the first couple weeks of class. Second, it's one of the most qualitative concepts we cover. You're more used to quantitative concepts because they do constitute most of the class, and so they can tend to get fall by the wayside. Yeah, equilibrium eats up a ton of this course. Like a surprising amount of this course gets eaten up by equilibrium. But it makes sense. Like it's a very diverse field. There's lots of questions that could be asked. All right, you're all very welcome. All right, so it's 1:46. Let's go ahead and sign off. You got one more live stream this Wednesday. After that, no more live streams. It's the end of the semester. Again, I'm available by email by chat via Teams. I'm going to kind of refrain from doing any type of video conferencing. If you really need it, we will. For lab practical, we're going to need to know which labs to study for. Technically, all are covered for the lab practical. It's going to borrow very heavily from Le Chatelier's and earlier. So this lab practical going to be much more heavy to the stuff that you did prior to the pandemic. This week is lab practical, so not right. Yes. So there is no lab this week. It's just the lab practical. That would have been the lab you would have done this week anyway. Again, you have until Friday at 5 o'clock. That said, Blackboard will cut you off. So if you try to take it like Friday at 4 o'clock to get in the last minute, it's not going to let you take it. You get an hour and 70 minutes. So Friday at 2:10 p.m., it will cut you off. You can no longer take the practical. Because I've given you so much time for the practical, I'm not going to grant extension unless you can really show you were like in the hospital this week. All right, you're welcome for the live stream. So yeah, Wednesday, last live stream. Again, not meeting with students on live stream unless you really need it. But even then, I'm going to schedule a time to talk to you. So got a lot going on next week. The goal is to get the grades up as fast as possible. I know you want to know what you got. I know that these grades need to be submitted as soon as possible. So yeah, keep in contact with me. But otherwise, I will see you all Wednesday. Thanks for showing up.